So far in the course, we've focused on the idea of pure programming in Haskell. So we haven't considered any side effects, we haven't considered any interaction with the outside world, and we haven't even written a simple hello world program. And the reason we've been focusing on pure programming is I really want to emphasize to you a new way of thinking. So many of you have probably done quite a bit of imperative or state-based programming before, but this course is about functional programming in Haskell, and I wanted to place the emphasis on this new way of thinking in terms of pure programming. But now we're going to see how you can actually do some impure programming in a language such as Haskell. And concretely, what we're going to be looking at is chapter 10 from the book, Interactive Programming. So the starting point for today's class is what we've been doing so far. So to date, what we have seen is how Haskell can be used to write so-called batch programs. And this is an old-fashioned term, but what it simply means is programs that take all their inputs at the start and give all their outputs at the end. So a batch program is essentially just a normal mathematical function of the kind which you can implement in a pure functional language such as Haskell. So this is illustrated in the diagram at the bottom of the slide. So a batch program simply takes all its inputs at the start, processes them away silently without interacting with the outside world, and then it's giving back all its outputs at the end. And if you want to think about a real-life example of a batch program, that's actually not as easy as it used to be, but a classic example in computer science would be a compiler, such as the Glasgow Haskell compiler. So a compiler takes an input, which is your source program, it translates it down to some kind of machine code silently without interacting with the outside world, and then it's going to give that low-level machine code program as its output. So this is what computing used to be like in the olden days. It was mainly writing these batch-style programs which don't interact with the outside world. But today, what we would like to do is see how we can also use Haskell to write interactive programs which read from the keyboard and write to the screen and interact with the file system and the disk and so on as they are running. And this is what most programs are like today. I mean, if you end up working as a professional developer in industry, almost all of the programs which you'll be writing are interactive programs which interact with the outside world as they are running. So again, we have a simple picture at the bottom of the slide here. An interactive program takes some inputs at the start, gives some outputs at the end, but crucially, while the program is running, it's also allowed to interact with the outside world. So it may be reading keys from the keyboard, maybe printing things on the screen, maybe accessing the network, and so on. So most programs are like this today. So if we want to write real programs, we need to figure out how we can do this kind of thing in a pure functional language such as Haskell. So it turns out that there's a bit of a problem here, and the problem is due to the nature of Haskell. So in Haskell, programs are simply pure mathematical functions, and that means they take all their inputs at the start and then they silently process them and they give all their outputs at the end. So in other words, Haskell programs do not have any side effects. And we can see this already just by thinking about a simple example. So for example, if I give you a Haskell function and it had type int arrow bool, then you know a few things about it. So you know it's a function, you know it takes an integer as its input, and you know it gives a boolean as its output, but crucially, you know that it's a pure mathematical function. It doesn't do anything other than take an integer and deliver a boolean. In particular, it's not allowed to have any side effects. And the problem here is that doing things such as reading from the keyboard and writing to the screen or interacting with the network while the program is running, these are all side effects. So in conclusion, interactive programs have side effects, but Haskell programs have no side effects. So there's a bit of a tension here. It seems that if we want to retain the purity of the Haskell language, we can't actually write interactive programs because that depends on having side effects which interferes with that. So What I'm going to be talking to you about today is the solution which was developed by the Haskell language designers. And the idea is that interactive programs which interact with the outside world while they're running can be written in Haskell by exploiting types. And the idea is a very elegant and a very simple one. We're going to be using types to distinguish pure expressions which do not have side effects from so-called impure actions which may involve side effects. So we're using the type system to keep the pure and the impure worlds separate. So the way this works in the language is actually very simple. So there's a built-in type called IO of A, which simply comprises the type of actions that return a value of type A. And again, the difference between an action and a normal value is that actions may also involve side effects. So if I have a Haskell program and it has type IO of A, eventually it will deliver me a value of type A, but along the way it may interact with the outside world as well. And just to make a small historical comment there have been many solutions to the problem of introducing interaction into a language like Haskell over the years, but actually the one we're going to be looking at today has been in place for many, many years, and this is the right fit for a modern functional language such as Haskell. So just to give you a little example of this, so here we have two examples here. If I have a program and it has type IO of char, that is going to be a program that's going to ultimately return me a character, but along the way could involve some interaction with the outside world. So IO of char is the type of actions that eventually will return me a character. And in the blue box at the bottom of the slide, here we have IO of empty. So this is the type of purely side-effecting actions or purely side-effecting programs that do not return a result value. So if you had a program of type IO of empty, you would execute it purely for its side effects. It wouldn't actually give you any meaningful result value, or in fact it would give you back a void result value. And actually, just a small technical note at the bottom here, the open round brackets, close round brackets is actually the type of tuples with no components. It's the empty tuple in a language like Haskell. So we can return to our example we had a moment ago when we were thinking about a function of type int to bool. We know it takes an integer, we know it delivers a boolean, and that's all it can do. It can't actually interact with the outside world at all. So now we can think about another example. If we had a function from type int to IO of bool, then that's a different kind of function. This time around, it still takes an integer and delivers a boolean, but because we have the IO tag on the output, it could also interact with the outside world while it's running. So a function of type int to bool is a pure mathematical function. It just takes an input, processes it, and gives an output. Whereas a function of type int to IO of bool could also, if it wishes, interact with the outside world while it is running. So now that we've seen the IO type, we need to think, how do we actually write interactive programs using this? And what Haskell provides us is with a number of basic actions or basic building blocks which we can use or combine to write interactive programs in a simple way. So the standard library provides us with a number of actions, including the following three primitives. So the first one of these is very, very simple. So the action called getChar, it reads a character from the keyboard and it actually waits for you to type one if you haven't typed one already. Then it echoes it to the screen, which simply means printing it to the screen, and then it returns the character as its result value. So if we look at the type in the blue box at the bottom of the slide, what we see is that getChar is an action which returns a character. So it's got type IO of char. So we know it's an interactive program and eventually it's going to deliver us back a character. And it's interesting to note, if we didn't use the IO tag here, then this program would not be able to interact with the outside world. So if I tried to have a primitive called getChar, and it simply had type char rather than IO of char, the only thing that getChar could be was a constant. It could maybe be the single character A in single quotes, because it wouldn't be allowed to interact with the outside world, because if you have something of type char, it has to be a simple constant. whereas getChar has type IO of char, so it's permitted to interact with the outside world. So the second primitive is exactly what you expect. It's the dual of the first one. So putChar is a function that takes a character and then it's going to build you an interactive program which writes it to the screen. So the action putChar of C writes the character C to the screen, and actually that's always going to succeed, so it's not actually going to return a result value, or really it's going to return a void result value. So again, you can look at the type to understand what's going on here. So putChar is a function. It takes a character as input that you want to print on the screen, and then it's going to build you a purely side-effecting action of type IO of empty that when you run it, it will print that character on the screen. So entirely straightforward. So the last one looks a bit strange at first sight, but we'll see that it's absolutely central to writing interactive programs in Haskell, and it's a function called return. And what return does is you give it a value and it simply returns the value v without performing any interaction. So we can look at its type. So return is a function. It takes a value of type A and then it's going to convert it into an action of type IO of A. And that action is simply going to return the value v without performing any interaction at all. So again, you might think, why would we actually need something like this? Well, it's really kind of a type conversion. It's moving from the pure world of values of type A into the impure world of values of type IO of A. So it's like a bridge from pure to impure. And we'll see that this turns out to be very important. Crucially, there isn't a bridge back. Once you're in the impure world of values of type IO of A, there is not a function that gets back to values of type A. So there's no bridge back from impure to pure. Well, actually, I'm not quite telling the truth here. Haskell does have a primitive called unsafe perform IO, which does exactly that. It's a bridge from impure back to pure, but it's not something you're really supposed to use as a programmer. It's really for internal use within the Haskell compiler because it breaks the purity of the language. So as a programmer, what you should think is you can go from the pure world into the impure world using return, but you're not supposed to go back. So now we have seen the three basic actions or building blocks. We've seen getChar, putChar, and return. And we can ask ourselves, how do we actually use these to write interactive programs? And the idea is very simple. We're just going to sequence these kind of actions together. So a sequence of actions can be combined into a single composite action by using the keyword do. So this is illustrated by the example in the blue box on the slide here. So the type, first of all, says we're defining act, which is going to be an impure action, and it has type IO of pair of char, which simply means it's going to deliver us a pair of characters, but along the way it can interact with the outside world. And the way it does this is by doing 4 actions one after the other using the keyword do. So the first action is we're going to read a single character using getChar, and we'll call that character x. So you see the syntax here for grabbing the result from the getChar primitive. In the second line, we're also going to read another character, but this time I haven't named it, so that will just be chucked away. In the third line, I call getChar again, and I'm going to call the resulting character y. And then finally, I'm going to return those 2 characters x and y as the result of the overall program. So again, this is an interactive program. It's actually going to read 3 characters, throw away the second one, and return the other 2 as a pair. And just a couple of points to note again here. Notice that after the do, I have lined up in the same column all of the 4 actions. And this is something you need to always do with the keyword do. After do, you can write a sequence of impure actions, and they all need to line up in the same column. So technically, what's called the offside rule, which we covered right back at the start of the course, is applying here. And the offside rule allows you to eliminate things like squiggly brackets and semicolons. You just use layout to make clear to the system what things should actually mean. And the second point, note that when you call a primitive such as getChar, naming the result is optional. So I named the result x and y in the first and third case, and I didn't actually name the result in the second case, and that's quite fine. So now what we can do, that we have these three basic primitives and we have the sequencing construct, the do notation, is we can actually derive or define some other primitives from these basic building blocks. And actually the primitives which I'm going to show you now are actually part of the Haskell standard library, and this is exactly how they're defined in the library. So the first primitive here is going to read an entire string from the keyboard. So getChar reads a single character, getLine is going to read an entire string. So what getLine does is it's an interactive program of type IO of string, which is going to read the characters one at a time and then compile them into a single string. So how does it actually work? Well, getLine is going to do a bunch of actions. So we're using the do syntax here. So the first thing we're going to do is we're going to read a single character using getChar, and we're going to call that character X. And then we have a conditional expression. If the character is a new line symbol, that means somebody has just immediately pressed return, then we will simply return the empty list, or in this case, the empty string. Otherwise, we've successfully read the first character in the string, and that's called X, and then we're going to have an internal do or a nested do, and that's going to recursively read the remainder of the line by calling getLine, and it's going to call that resulting string X's, and then finally we're going to return the entire string by putting the first character X on the start of the remaining character X's, and then we'll return that at the end. And notice here we need to write return in the two cases. So we're returning the empty list and we're returning the non-empty list, and that's because everything inside one of these do blocks must be an action. So in the final line, if I forgot to write return and just wrote x:(x's), x:(x's) is a string. But we need to have an action there because it's in a do block, so we need to write return of that string. Okay, so this is the kind of reason why the primitive called return, which you might originally think, why do you need something like this? You need it in these kind of do blocks here. So here's another couple of examples of so-called derived primitives from the standard library. So this is just things defined in terms of the basic building blocks using sequencing. So the first is called putStir, and this simply writes a string to the screen. So you give it a string as its input, and it's going to build you a purely interactive program of type IO of empty that simply prints that string on the screen, one character at a time. And it's defined by recursion. So in the base case, we're simply saying if you want to put a string which has nothing in it, then all you're going to do is simply return the empty result value or the empty tuple. And in the recursive case, we're matching on the string. So X will be the first character in the string. X's will be everything else. And then we have a simple do with two actions. We simply put a single character X, and that will print that on the screen for us, and then we're recursively going to call putStir, and that will print the remaining characters on the string for us. So again, it's an example of a recursive program which is actually doing something with interaction. So the third example here is sometimes we want to write a string onto the screen and then move to a new line. So this is a simple way of doing this, which again is built into the standard library. So putStir line simply takes an input string X's, prints it on the screen, and then prints a new line character to move on to the next line. Okay, so we have these three basic primitives. getLine is going to read a string from the keyboard, defined recursively. putStir does the same thing, also defined recursively, and then we have a way of moving on to a new line as well. So we can give a simple example of this now. What we're doing here is we're defining an action that is going to prompt for a string to be entered, and then it's going to display its length. So it's not a very interesting program, but it just illustrates using these new primitives which we have defined and which are built into the standard library. So I'm defining an action called strlen for string length, and it's a purely side-effecting action, so it has type IO of empty. And it's defined by simply doing 5 actions in a row. So in the first line we say enter a string, that's emitting a prompt. On the second line we're reading a string of characters from the keyboard and calling that X's. And then in the third, fourth and fifth lines we're simply going to say the string has however many characters. So the way we're printing the number of characters, we're first of all just calling the length function, which will calculate how many characters are in the string, and that will give us a number back. And then we need to convert that number into a string. So we use a magic Haskell function called show, which takes more or less anything and prints it onto the or converts it into a string, so that we can then print that on the screen. So again, just a simple example of a purely side-effecting program, which is just prompting the user to enter a string and then telling us how many characters we have in that string. So we can actually try running this program in practice. So if you type this into the GHC system and you load it in and you type strlen to actually run it, then you can enter a string such as Haskell and it will say the string has 7 characters. So it does exactly what you'd expect. So just one small technical point here. When you evaluate an action, such as by evaluating strlen in the blue box here, what it does is it executes its side effects and the final result value is discarded. So in this case, actually, the final result value of the program is a void result, so there's actually no result value. strlen has type IO of empty, but sometimes you might be running an interactive program which say delivers a string or something like that, and when you run that it will execute it for its side effects and any final result value will simply be thrown away. So what I would like to do for the rest of the class is put everything that we have learned today into practice by implementing a simple interactive game. And the game we're going to implement is known as Hangman. So maybe not everyone's familiar with this, so I'll first of all just introduce you to the game and what the rules are. So it's a 2-player game, and first of all, one player is going to secretly type in a word in a way that the other player can't see it. So we're going to need to write a program which actually lets one player secretly type in a word, which we'll do in a moment. Then the other player is going to try and deduce the word by entering a sequence of guesses. And then for each guess, the computer is going to indicate which letters in the secret word appear in the guess. And then, of course, the game is going to end or be finished when the second player actually guesses the secret word. So we're going to be writing an interactive Haskell program that implements the game of Hangman, and this time around we're going to adopt a top-down approach. And what I mean by this is we'll implement the top level part of the game first, and along the way we'll assume we've got some helper functions available to us, and then we'll implement those helper functions later on. So we're going to start right at the top level then. So we're going to implement the game of Hangman, and this is going to be a purely interactive program. So it's a program of type IO of empty. We purely execute it for its side effects. So the top level program is a simple do block with 4 actions in it. So the first action simply prints a string which says to the first player, think of a word. And then we're going to read this from the keyboard in a secret way so that the second player can't see it. So we're going to have a helper function called sGetLine, which stands for secret getLine, and that's going to read a string of characters from the keyboard in a way that the second player can't actually see it. So we'll implement that function later. So we'll call sGetLine and we'll call the secret word, which the first player enters, we'll call that word. And then we're emitting a prompt to the second player which says try and guess it, and then we're going to enter a function called play, which is going to be our main game loop. This is going to be the function that actually implements the main part of the game, and we're going to pass in the secret word as a parameter to the play function. So first of all, we can think, how do we implement this action called sGetLine for secret getLine, which is going to read a line of text from the keyboard. And what we're going to do is, just like when you type your password in when you're logging in, it's going to echo each character as a dash so that someone can't see what you're typing in. So in the blue box here, we have the definition for the secret getLine action, and it's basically the same as getLine, except it doesn't do echoing of the character that you type. It's going to echo everything as a dash. So let's understand how the actual definition for this works. So it's a do block, as you would expect. And the first thing in the do is we're going to read a character from the keyboard without echoing it. So we're not calling getChar here, we're calling another helper function called getCh, which we're going to write in a moment, and that will read a character without echoing it to the screen. And then, as before, we're going to check, has someone simply hit the new line symbol? And if they have, we're going to print that symbol. We'll actually echo it so that we actually move on to the next line, and then we'll simply return the empty string because nothing has been typed. And then otherwise, in the else, we have another do block, and we're simply going to echo a minus sign or print a minus sign because somebody has typed in a character and it hasn't been echoed, so we want to just reflect that somebody has typed something by emitting a minus sign. Then we will call ourselves recursively to read the remaining characters in the string, and we'll call that x's, and then finally we will return the full string, which is comprised from the first character x and the remaining characters x's. So in order to complete the game, we need to define the two helper primitives which we've used. And the first of these was called getCh, and it's an action that reads a single character from the keyboard without echoing it to the screen. And that's so that the other player can't see what the secret word is when the first player is typing it. So what we've got in the blue box is, first of all, we're importing a library called system.io, because I need a primitive from that library, which we're going to be using below. And then we're defining getCh. And getCh is an action because we have the IO tag, and it's going to return as a character. So it's got type IO of char. And then the way getCh actually works is it's a simple do of a sequence of actions. So what we're doing in the first step is we're turning off echoing on the standard input channel. So hsetEcho is a primitive from the system.io library. It takes an input channel or an input handle as its first parameter, so we're passing in the standard input channel here. Then it takes a flag or a boolean that tells us whether we want to turn echoing on or off. In this case we want it off, so we pass in false. So the first line just turns echoing off on the standard input channel. Then in the second line, we're simply calling getChar to read a character from the keyboard, which will not be printed on the screen now because echoing is turned off. In the third line, we turn echoing back on by calling hsetEcho with the standard input channel, and this time we pass in true to say we want echoing turned back on. And then in the final line, we're simply going to return the character x, which we've read from the keyboard. So overall, what getCh is going to do is it's going to read a character from the keyboard without echoing it to the screen by the idea of turning input echoing temporarily off while we read that character. So the second thing we need to think about defining now is the function called play, which implements the main game loop. So what this is going to do is request and process guesses until the game ends. So let's look at the type first of all. So play is a function. It takes a string as input, which is going to be the secret word, and then it's going to be a purely interactive program which is going to be executed for its side effects and doesn't actually return any meaningful result value. It's just going to return a void result. So how does it actually work in practice? Well, the play function takes the secret word as its input, and then it's going to do a sequence of actions. So the first action is we're just going to print a simple prompt, in this case a question mark, and this is going to indicate to the second player that they're supposed to make a guess at this point. Then we're going to call getLine, and that will read a string of characters from the keyboard, and we're going to call that guess. And then we're going to have finally a conditional expression, an if then else. So what we're going to do is we're going to check, is the guess actually equal to the secret word? If it is, then the game is finished. So we just print out a message. So here I've decided to print you got it. Otherwise, what we're going to do is we're going to call another helper function called match. And what match is going to do is you pass it in the secret word as the first parameter and the player's guess as the second parameter, and it's going to indicate which letters are correct and which letters are incorrect in some way or another. And then it's going to print that string on the screen using putStir line. And then finally, in the last line here, we're going to call ourselves recursively, and we'll call the play function with the secret word as input. And just a point about how this main game loop is structured here, notice that I'm having to pass the word in as a parameter at the start of the function, and right down at the end where I call myself recursively, I'm also calling the function with the same word as the parameter. And this is quite different from the way that you would do this in a traditional imperative language if you were writing a hangman game. There, the main game loop would typically be structured by having word, or the secret word, as a global variable, so you don't need to pass it in. But in Haskell, we don't have any global variables. It's a pure functional language. So if we want the game loop to have access to something, in this case, the secret word, then we need to actually pass it in as a parameter. So this is a kind of key difference between how you structure programs as an imperative programmer and as a pure functional programmer. So to finish off the implementation of the hangman program, all we need to do now is implement the final helper function called match. And there's many different ways that we could do this, but what I've decided to do here is have the function indicate which characters in one string occur in another string. So we can see a simple example of this down at the bottom. Here I'm matching the string Haskell against the string Pascal, and what's happening in the output is for each of the characters in the first string, we're going to think, does it appear anywhere at all in the second string? If it does, then we'll output the character, and if it does not, we'll output a little minus sign. So this is one possible way to kind of do some kind of approximate matching between two strings. So then what you see in the box at the top is how we can realize this as a Haskell program, actually in this case implemented using a list comprehension. So all we've got on the right hand side is where we have a simple generator which is taking each character X one at a time from the first input string X's. And then on the left hand side we're simply having a conditional expression which checks for each character X, is it an element of the second input string Y's. So lm is a library function that takes a thing and a list of things and tells you is the thing appearing anywhere in the list. So in this case it's checking is the character X an element of the list Y's. If it is, we keep the character X, we output it, otherwise we're going to output a minus sign. So this list comprehension realizes the kind of behavior we see in the example at the bottom. But again, there's many different ways that you could decide to implement the match function. So you might want to play about with some different definitions yourself. So that concludes the implementation of the hangman program. What I'd like to do now is give you a simple example or show you it running in practice before we move on to think about the exercise for today's class. So what I've done now is I've loaded the hangman program into GHCI. So we could start up an editor and we could have a look at the code, and this is just all the definitions which we've written today typed into a single file so that we can run it. And before we actually run it, I'd just like to comment on the balance of this program in terms of how much impure code there is and how much pure code there is. So if we look at the code, almost everything that we wrote today was impure or involved interaction with the outside world. That's all of the code there in blue. It all involves the IO type. Whereas the only pure piece of code which we wrote today in the hangman program was the match function down the bottom. Everything else is impure or side effecting code. And this is actually quite unusual from the point of view of a Haskell program. Most Haskell programs are almost entirely pure code, and then they have a thin wrapper of impure code which interacts with the outside world around the edge. So this is quite atypical from a real Haskell program. So let's have an example of this thing actually running in practice. So I just type hangman and that will start the game up. And then I have to think of a word, and my secret word is going to be my favorite programming language, Haskell. And then someone needs to try and guess what it is. So they could type in some other programming languages, Basic, Python, Pascal, Java, and so on. And then finally, someone gets it right and it says, you got it. So this is an example of how you can write a simple interactive program in Haskell. I fully appreciate this is not a tremendously interesting example, but it illustrates in a simple way the idea of how you can write impure or interactive programs in a pure functional language such as Haskell. So what we're going to do now is just quickly move back to the slides again, and I'd like to talk you through the exercise from today's lecture. So here is the exercise for today's class, and it's to implement another game in Haskell, and it's called the game of nim. And before I explain the rules of the game, I'd like to tell you what I'm going to do next time around. So in the next class, I'm going to do a live coding session where I show you how to solve this exercise. But maybe you want to have a go at it yourself before then, so I'd like to actually explain the rules of the game to you now so that you've got a chance to try it for yourself before I show you how to solve it next time around. So nim is a board game, and the board in this case is going to comprise 5 rows of stars. So in the first row we have 5 stars, then 4, 3, 2 and 1. If you've seen the game of nim before, there's different configurations of the initial board, but this is the one that we're going to work with for our program. And then it's a 2-player game. There's 2 players who take it in turn to remove 1 or more stars from the end of a single row. So for example, if I was the first player, I might take 3 stars off the end of the first row, and then the second player might decide to take all the stars, so all 4 stars from the second row, and so on and so on. So you can take as many stars as you like from the end of a single row. And then the game ends when one player removes the last star or stars from the board. So if you're the player who makes the board empty by removing the final star or stars, then you are the winner. So I suggest you maybe try and have a go at implementing this for yourself using the techniques about interactive programming that we learned about today. But I'm going to show you how to do it anyway in a live coding lecture next time around. But if you would like to have a go at it yourself, here is a hint. And what I would suggest to you is that you represent the board as a list of 5 integers that give the number of stars remaining on each row. So for example, the initial board, which we had here, had 5, then 4, 3, and 2, and 1 stars. So you could represent that by the list 5, 4, 3, 2, 1. So that's it for today. We've seen how you can write interactive programs in Haskell, and here's a little challenge problem for you. Try and implement the game of nim for yourself using what you've learned today, and I'll show you how to do it in a live coding manner next time around. So that's it for today, and I will see you again next time.